Hello, good evening, all. Am I audible, everyone? Hello. What about others? Okay, Rakshita joined. Yeah, Sai and Rakshita, how many sessions are completed from your side?
5, ma'am.
Yeah, hello. All Verilog sessions completed, recorded sessions?
No, ma'am, one more session.
One more session. Okay. So what you want to see, like which topics are left? Have you gone through the procedural assignment statement, continuous assignment statement?
Going on, ma'am.
Okay, okay. Um, so any doubt still here
No,
in
no, ma'am.
combinational logic circuit, flip-flops, registers? Sai, for you, did you completed all the sessions?
I completed.
Okay,
Yeah. I have to go through it sequential once more.
okay. Any doubts?
As of now, no, ma'am.
Okay. So today we will discuss on counters in digital electronics. Okay, and we will discuss blocking assignment statements, non-blocking assignment statements. Before we have discussed till procedural continuous assignment statements, begin and blocks, fork joins, so how the serial execution, parallel execution we have seen. So the leftover topics in Verilog or mostly blocking and non-blocking assignment statements. What is meant by a latch? Why do a latch infer in the digital logic design, and how we can avoid the bad latches? That's the one topic. And blocking, non-blocking assignments we will discuss today. And swapping operation, generate block we will discuss in the next session. UDPs are there. UDPs are not much important. These are very old style. Okay, just how we design a test bench directly. It's an old style, but we will discuss UDP, the programming style and all. Next to test benches concept, these are leftover. Test bench concepts will take one day. Okay, today we will complete counters theory part and also blocking, non-blocking assignments. If time is there, we'll complete what is meant by a bad latch. How can we avoid the bad latch in Verilog? Okay, these three topics will complete today. In the next session, we will discuss on counters programming part, all different types of counters, how to design up counter, down counter, and also a few important like logically how we can write a simple programming. Okay, counters will take one day. Generate block is also simple topic. Generate block UDP simple topic. We can take just 10 to 15 minutes for that. And okay, today counters. Next session counters Verilog programming, and coming session we will clear out with test bench concepts, all simulator directives. Dollar display, dollar monitor, dollar strobe, dollar write, dollar dump file, dump files, dump on, dump off. So all these things will take one day. So three sessions. Next, fourth session, finite state missions. Theory one day. Okay, digital logic design theory one day. Uh, coding one day. Finite state missions. So total five sessions. And then memories. Memories theory, practical, mostly 1 or 2 days. Okay. So total seven sessions hardly. We will discuss 1 or 2 days for only practical programming. Okay, and so today is 14, right? mostly by end of February or March first week, we will complete the Verilog HDL. Okay. If any leftover topics are there, any programming, extra programming is there, we will discuss all the things. And also we need to complete one protocol, one project in Verilog, right? So mostly March first week, we are going to complete Verilog digital electronics. And in digital electronics, leftover topics are glitches, hazards, and static timing analysis, CMOS design. So glitches, hazards also will come into the static timing analysis, and setup time, hold time analysis, delays or their contamination delay, propagation delay, all these things also comes under static timing analysis. So it takes hardly two sessions, CMOS design, static timing analysis. Okay, so if possible, we will complete on Sundays, static timing STA and CMOS design, and some digital questions, mock questions, and Verilog mock questions we will discuss on extra Sundays. Okay, but by March first week we will complete all the Verilog syllabus. This is our next half part. So till now half part completed. Next we need to complete half Verilog. Okay, so everyone, whatever the doubts you have till now, try to clear all your doubts and do the assignments. You can revise the recorded sessions one more time. Okay, so whatever the doubts you have, try to revise all the recorded sessions. If you are interested further to do more projects, okay, internship batch is going to start. You can involve with the internship students also. Okay, we are discussing, we are working on good projects in Verilog HDL. So I will show you some projects in internship batch. You can involve because Verilog you will be completing by March first week. So project one is 32-bit 5-stage pipeline MIPS processor, one of the best project in processor related, and also RISC processor. And these two are processor related. You can select either MIPS or RISC. And third project is high-speed serial CRC design for real-time applications. Fourth one, dual address ROM for high-speed memory access. And fifth one, Radix for restoring division algorithm for efficient digital signal processing. And 16th one also related to MIPS processor. And sixth and seventh also, it is a multiplier. In digital electronics we have different types of multipliers. Okay, so that would be the seventh project. And eighth one is booth multiplier. Seventh one Wallace tree multiplier. Eighth one booth multiplier. And ninth one CRC design. And 10th RAM implementation. Okay, so better I can suggest one multiplier. You can select either booth multiplier or Wallace tree multiplier, any one multiplier. And one processor related, select one or two, any one project from 1 and 2, and select any one project from 7 and 8. Okay, so from tomorrow onwards, this internship batch is starting. You can work from tomorrow itself. First we will discuss theory part. Okay, or else if you want to start after completion of Verilog, total Verilog, you can start from March 15th, March 15th. Okay, you can start from tomorrow onwards or March 15th onwards, your wish. Okay, decide yourself and let me know. Better you can start March 15th onwards. These 1 month you can concentrate purely on Verilog. Okay, and also finally we are going to discuss one protocol and one project. You can concentrate on that. From March 15th to April 15th, you can concentrate on this project. This is just extra project I want to give. Okay, not in curriculum, just for your practice. Okay, clear everyone? Hello.
Yes, yes, Prashant.
Okay. Next, okay, digital logic design. Today we will discuss on counters part. So have you gone through these counters? What is mean by a counter? What is the use of counter and applications of counters? So what is mean by a counter and why do we use the counter and why JK flip-flop is used in counters? Why don't we use any other flip-flop? And what are the different types of counters and applications of counters? Hello. Rakshita, Aditi, Sai, Vinita, Suma.
Yeah, it counts the number of clock cycles, actually, how many number of clock cycles are required for the data transfer. We need to count because for that purpose.
Okay. Others? Okay. So counter in digital electronics. Basically, counter is used to count number of clock cycles. Whether it is a asynchronous counter or synchronous counter, we have two different types of counters, synchronous and asynchronous. So what is the difference between two? Synchronous in the sense all will be triggered at a time, all will be in one connection, only dependent on clock. All the flip-flops or all blocks will be dependent on one clock signal. Asynchronous means it doesn't have the clock. Even if it have the clock, that clock will be given from the one circuit output to the input of another clock. Okay, so that's how we have two type of counters, asynchronous and synchronous. In that also we have different type of counters like a positive edge triggered counter, negative edge triggered counter. Positive edge triggered counter means at every positive edge of the clock only the output will be changing. Okay, so that's why we call it as a positive trigger counter or negative trigger counter. And in that we have up counters, down counters, up down counters, or modulo counters. Like there are different type of counter, but whatever the counter, the final output is, the main application is to count number of clock cycles. Okay, already told you. Mostly in the applications like a digital watch. In digital watch we use the counters, right? I think on the first session I discussed the counters example. So 3-bit counter means how many clock cycles it will count? 3-bit counter means 2 power 3 number of clock cycles. Whether it is a up or down. Up counting means 0 to 7 till 7 it count. Down counter means 7 down to 0 it will be counting. Like that 4-bit counter. 4-bit counter means 4 bit. 4-bit means 4 flip-flops. We need to connect the 4 number of flip-flops. Each flip-flop will store 1 bit data. Okay, so like this. In terms of connection, so how it is connecting? If it is a synchronous counter, the clock will be common to all these. If it is not synchronous, output of one flip-flop will be connected to the input of another flip-flop. That's what we call it as a clock connection. Okay, that is difference between synchronous and asynchronous. Positive edge trigger, negative edge trigger means if you want to change the output with respect to the positive edge, then this clock will be like this positive edge. If you want to change with respect to the negative edge, it should be symbol like this bubble. That means negative edge trigger. Okay, we will see different type of counters. So 4-bit means 2 power 4, total 16 clock cycles. It will be counting 16. Up count means 0 to 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Down count means 15 down to 0. 15 counter. Okay, so whatever the counter you chosen, like a 3-bit, 4-bit, 5-bit, 6-bit, based on that it will count to power n number of clock cycles. Okay, that is fixed, 0 to 2 power n number of clock cycle. But sometimes you may not require all number of clock cycles. Okay, suppose 4-bit counter is there. 4-bit counter means it will count 0 to 15. Okay, by using 4-bit counter, maybe you want to design a decade counter. Okay, decade counter means what? Only 10 number of clock cycles it will be counted. That means 0 to 9 number of clock cycles only it will be counting. Decade counter. Like that BCD counter also same, 0 to 9 number of clock cycles only it will be counted. Or else you want to count only 0 to 6 number of clock cycles, so we call it as a mod 6 counter, 0 to 5. Mod 14 counter, mod 20 counter, mod 10 counter, or mod 2 counter, mod 7 counter. So based on how many number of clock cycles you want to count, 0 to 6 mod 7 counter, that means total 7 clock cycles it is counting. 0 to 5 only you want to count. 0 to 5 means total 6 clock cycles it is counting, so we call it as a mod 6 counter. Okay, so what are the real-time applications? Suppose I told digital watch, right? A digital watch means how many number of hours, like a 24 hours, 59 minutes, 0 to 59 minutes, 0 to 59 seconds. Okay, so if you see here, 24 means which counter? It comes under 5-bit counter, right? 2 power 4 means 16, 2 power 5 means 32, so it counts 0 to 31. But in this 0 to 31, all the clock cycles are not required. We no need to count 0 to 31, just 24 till 24 enough. So it should count 0 to 23 only. 24 clock cycles means 23 only. Okay, like that here 59 means a 6-bit counter. But in the 6-bit counter, we no need to take all the values till 64. We just need to stop at 59. So we designed a mod 59 counter here, like that mod 59 counter. So how can we design a modulo counter? We need to see that. Okay, so like this for counters, like or else any project, whatever the project you have taken, everywhere there will be a requirement of counters, registers. As I told you before in the last session, suppose there is a processor. Okay, like SOC, there is a SOC and there is a processor here. This processor, you are communicating with some other chip. Suppose there is a USB protocol, USB bus. In your laptop, you will be connecting some USB cable, right? To this USB cable, sometimes you will connect your mobile phone or some joystick or extra keypad or mouse pointer. All these things you will be communicating. Okay, so how this communication will be happen here? Serial communication, wire, through wire only you are connecting. There will be a cable, through the cable you are communicating here. So mostly the data will get serially 1 0 1 1 0 1 00, like that serial communication. But same data will be communicated to your processor also. Okay, but here processor never receive the data serially. It always communicate parallelly. The processor, if it is connect to the memory block, and the processor will communicate with the graphic processor, and some bridges will be there, north bridge IO, south bridge IO, and there will be a lot of peripherals. Okay, internal each here it may communicate serially, internal devices. Okay, but at the final stage, processor, near processor communication, we use parallel. Okay, so there in this time there will be a requirement of parallel to serial communication. So we need to use parallel to serial shift registers or serial to parallel shift registers. These type of registers requirement will be there. Okay, like that. Suppose counters, how can we use the counter? Suppose for here processor is need to transmit 128-bit data. Okay, processor is working with a 128-bit data, and this 128-bit data, it should transmit to your mobile phone. Whenever your laptop is connected to the mobile phone, you are exchanging some data or you are exchanging some files. Okay, so if it is transmitting 128-bit data, if your mobile phone receives only 64-bit data, it never work. It's wrong, right? So whatever the processor is transmitting here, your mobile phone should receive same. Or whatever your mobile phone is transmitting to this processor, the processor need to receive same. Okay, both should be same size. Whatever the bit number of size or in terms of memory, whatever. Okay, so how we will count this 128-bit data at the processor side or even in a memories or even in a protocol, USB protocol, your protocol, I2C, APB, AHP, AXI, whatever the processor like a MIPS processor or RISC processor, even multipliers, you are going to work on multipliers, right? Also, whatever, there will be a requirement of uh, counting number of bits 0 to 128 bit or 0 to 127 bit we need to count here. Okay, so why we are using the counter in the sense to just for confirmation, for easy purpose, you are transmitting the data to each clock cycle, each location. Suppose there are 128 number of locations. So to 0 to 120 number of locations, how you are sending the data to the memory? So first you are starting with the 0th clock cycle. So to the 0th location, you are passing some data. Next to 0 plus 1, first clock cycle. 1 plus 1, 2. 2 plus 1, 3. 3 plus 1, 4. 4 plus 1, 5. 5 plus 1, 6. 6 plus 1, 7. Like that till 128 number of locations you are storing the data. So to transmit from 0 to 128 number of locations, here counter logic is important. Counter will work as a pointer 0 to 120 number of locations. In C language, maybe you have written some basic codes like a pointer plus 1, pointer equal to pointer plus 1. So it will be incrementing every time plus 1 plus 1. Same way, the counter is used here. In hardware, we call it as a counter to count the number of clock cycles. Okay, like that every protocol. Suppose in Verilog you are going to design a UART protocol. UART is also same as USB protocol, but UART is a basic version. USB is a present generation we are using USB protocol, but in old and UART protocol is a very old version. Okay, it's a basic first protocol. Okay, so there how we will store the data, how we'll pass the data, only 8-bit data we can send. But nowadays through the USB protocol we are able to pass 128-bit data or 256-bit data, like that huge amount of data. But by using UART protocol we can transmit only 8-bit data. So this 8-bit data, whether we sending from transmitter side to receiver side, whether it is sending properly or not, maybe sometimes you may send only 6-bit data, remaining 2-bit data maybe we forget, but system won't forget based on the counter logic, because we will tell that counter should be equal to 8, then only it should stop the transmission, because here it is storing 8-bit data. So whenever counter is greater than or equal to 7 or greater than 7 or equal to 8, then we can tell it counter should be stop, the functionality should stop, because we already passed 8-bit data. Okay, like that in most of the cases we write the counter logic every project. But how we need to write the program? However, we see suppose here we are using the block diagrams like this. These type of block diagrams till now we have designed in a structural modeling, creating one flip-flop, By using that flip-flop, we took multiple copies and written the program. That's a huge complex code in structural modeling. But in real time for projects, we never use those type of coding style. Okay, we need to use a simple logics, behavioral modeling to design just simple counter logic, count equal to count plus 1, like that. Up down counters, how we need to design. Yesterday I have shown you some assignment like a 1 counting 4 times, 2 4 times, 3 4 times, 5 5 times, like 1 1 time, 2 2 times, 3 3 times, 4 4 times, 5 5 times, like that. How we can use different type of counters, we are going to discuss in this uh, today, just theory, and coming session we'll implement in Verilog HDL. Okay, any doubts still here?
Oh, ma'am.
Any other doubts? No? Okay, fine. So I think everyone understood what are the what is the use of counter, and what are the different type of counters and applications of counters, right? Next, why JK flip-flop is used for the counter. Why JK flip-flop? In the sense, in JK flip-flop, we don't use all the conditions, like we have memory state, reset state, set state. We don't use these 3 states. We just use toggle condition. Toggle condition means in place of JK flip-flop, you can use T flip-flop directly, or else J equal to 1, K equal to 1. In that case also, it will work as a T flip-flop, toggle flip-flop. Okay, so toggle in the sense, it counts number of clock cycles. I will show you how it counts number of clock cycles. And also we call it as a frequency division circuit. T flip-flop as a frequency divider. Okay, so if you see the theory part of counters, so as the name suggests, it counts number of clock cycles and sequential manner to count number of clock cycles, and also random manner. And coming to classification, we have 2 type of counters: synchronous, asynchronous, pausage, negate, binary, decode, and decade, and up down counter, up down. And by using flip-flops J, K, T. D we never use, very rare, mostly J, K, T. Okay. Next, concept of frequency division. So what is the concept of frequency division? Can anyone explain?
If we want the frequency to be divided by 2, let's say it is 100 hertz, but we want it to for 50 hertz, or any like one to do 1 by 3, 1 by 2, 1 by 4, whatever we need, how much ever we need.
Okay. Okay. So T flip-flop, when T is equal to high, toggle, T equal to 0, memory state, right? So toggle in the sense, if before state is a 1, next state will be 0. Before state is 0, then next state will be 1. If before state is 1, next state will be 0. Like that, it will change for every positive edge of the clock. Okay. So it always input will be 1 only. Then only we get the toggle condition. Here is the clock. Positive edge of the clock, positive edge of the clock. The output will be changing with respect to the posage. Okay. And the time period here, 10 nanoseconds. Time equal to 10 nanosecond means, how can we calculate the frequency? F is equal to 1 by 10 nanosecond. Then it is 100 megahertz. Okay. Like that, 1 by 5 nanoseconds or 1 by 20 nanoseconds. Like that, you can consider whatever. Now, output. So what is the output? Suppose initially output is 0. For next positive edge of the clock, if input is 1, output will be toggle state. So it will be 1 till which case, which point it will be 1. for next positive edge of the clock, because here output will be changing with every positive edge of the clock. So next positive edge of the clock, here again it do toggle 0. Next positive edge of the clock, again toggle 1. Next positive edge of the clock, here again toggle 0. Next positive edge of the clock, again toggle 1, 0. Like that it will keep on 0, 1, 0, 1 toggle condition. Okay, so frequency is a dividing here. So if you observe, time time will be increasing, that means delay will be increasing, frequency is reducing. Frequency reducing means what? Speed is increasing. Okay, time delay is more here. So 20 nanoseconds, 10 nanoseconds plus 10 nanoseconds, whole clock cycle is 20 nanoseconds. So frequency is dividing here. 50 nanoseconds, 1 by 20, 50. Okay, so like that, this is for one clock cycle. If there are more number of clock cycles, that means if you connect more number of flip-flops here, another flip-flop you have connected, and to this another flip-flop you have connected, and here another flip-flop you have connected, then what will be the output and what will be the frequency division? Okay, suppose here to this flip-flop the frequency is divided f by 2, and here the frequency will be divided f by 4, and frequency will be divided f by 6,
8.
and frequency will be divided 8. Okay, we will check that. Frequency will be divided f by 16. Okay, like that frequency will be getting divided for every flip-flop. Okay, so that's what we call as a counter, a synchronous counter and synchronous counter. So till now clear everyone till here?
Yeah, ma'am.
Any other doubts? No? Okay, fine. So coming to the asynchronous counter, in asynchronous counter is also known as ripple counter, same as ripple carry adder, because same operation, one output is connected to the another flip-flop input. So below 4-bit asynchronous counter, which is using T flip-flop. So classification of asynchronous counters, we have asynchronous up counter using pause edge trigger flip-flop. Up counter means based on number of flip-flops you are connecting. If you connect 2 flip-flop, 2 power 2, 0 to 3. 3 flip-flops means 0 to 7. 4 flip-flop means 0 to 15. Okay, down counter. Down counter means like 7 to 0, 15 to 0, down counting. But output will be changed with respect to the pause edge clock. Like that, asynchronous up counter using negates trigger. So at every negative edge of the clock, the output will be changed. Like the down counter using negate clock. So every every negative edge of the clock, the output will be changing. So if you see here how to write the first we will discuss for synchronous how to design, then you will get understand easily. Okay, first we will discuss asynchronous. No problem. Okay, if you see here, 3-bit asynchronous down counter. Down counter means you always need to remember this Q output of first flip-flop. Q will be connected to input of this clock. If it is a synchronous, only this clock will be connected to here. Okay, as you see here, in synchronous counter, the clock is common to all the flip-flops. But in asynchronous counter, the clock will be output of this Q2 here, output of this Q2 here. That is the clock signal input. For asynchronous down counter, positive edge triggered. If it is a asynchronous up counter, then Q bar is connecting to clock. Okay. In down counter, Q is connected to clock. In up counter, Q bar is connected to clock. Like that negative edge, reverse. Now it is reverse. For down counter, Q bar will be connected to negative edge of the clock. Here up counter connected to clock. But in negative edge trigger, this Q bar down counter will be connected to here. And for negative edge up counter, this up one will be connected to down. Okay, just a simple confusion will be there, but reverse. For positive edge, up one will be connected to down. For negative edge, up counter, it's same. Okay, for negative edge, down counter, down one will be connected. For positive edge, up counter, down one will be connected. Okay, the one both are same, like here down and up of negative counter, these both will be same, and up of positive edge, down of negative edge, these two are same. These two down will be connected, Q bar will be connected to clock. In this case, this Q will be connected to clock. Clear everyone? Next, like the Q to clock, and here Q to Q1, and here final output Q2. So total 3 bit. 3 bit means it counts 0 to 7. As it is a down counter, it counts from 7 to 0. Okay, so first input 1, every positive edge of the clock. Output is changing every positive edge of the clock. So what is the first flip-flop output? If input is 1, output will be toggle. So for this positive edge of the clock, initially it is 0. For this positive edge of the clock, output will be 1. And next again toggle 0. And next positive edge of the clock 1. And again positive edge of the clock 0, 1, 0, 1, 0, 1, 0. This one output of first flip-flop. Okay, second flip-flop, how do we get the output? For second flip-flop, this Q0 is the clock. Okay, so for second flip-flop, this will be the positive edge of the clock. It will be Q0 is the clock of Q1. So for every positive edge of the clock, output will be changing like this. Okay, so initially 0. First positive edge of the clock 1. Next positive edge of the clock 0. Next positive edge of the clock 1. Next positive edge of the clock 0. Again positive edge of the clock 1. Okay, and then for this clock output input is a Q1. So these Q1 positive edge of the clock, and here and here, these will be the clock input to the next Q2. Okay, so initially 0, next positive edge of the clock here 1, till next positive edge of the clock here 0, till next positive edge of the clock it is 1. Okay, clear everyone? Understood?
Yes.
So if you check here, initially 0, 0, 0. So output is 0. And here 1, 1, 1. So 7. Triple 1 means 7. 1, 1, 0. That means 6. 1, 0, 1. 5. 1, double, 0, 4, 0, double, 1, 3, 0, 1, 0, 2, 0, 0, 1, 1, 0, 0, 0, 0. Again 1, 1, 1, 7. That means 7 down to 0. Down counting. Down counter with respect to the positive edge trigger flip-flop asynchronous. Okay. Clear everyone? By next session, you need to write the program in structural modeling. How you will write the program? Very simple. Create the T flip-flop and take the copies of three flip-flops and pass the input 1 fixed input 1, or else you can generate from test bench also. Okay. Clock connections, you know how to connect the clock, and this will be the Q not output, and same output will be the input to the next clock cycle. Instead of putting this clock for next copy, you need to put this Q0 near clock, and third flip-flop you need to put Q1 as a clock. So if you check the output, you will get the clock cycles like this. Okay, that is a normal manual method, but we need not to consider that for counters, but practice. Okay, from your side. Clear everyone till here? Next, up counter. Same up counter also. So Q bar should be connected to here, and Q1 should connect to here. So with respect to the positive edge of the clock, every positive edge of the clock, initially zeros. So here, what is the output? First positive edge of the clock 1, then 0, 1, 0, 1, 0, 1, 0, 1. Next, this one positive edge of the clock, and here, and here, here, and here. So 0 initially, okay, sorry. Yeah, this diagram is wrong. In this PPT, both will be same diagrams. We kept same diagram for this and this. Both diagrams are same. We need to change that. But same 0, it should be triggered at every positive edge of the clock here. Instead of here, you should get like this. Like this. Okay. And here also, for every positive edge of the clock, initially 0, 1 till where? Till this positive edge of the clock. And till here. Till here. Okay. Now output will be 0, 0, 0, 0, 1, 1, 1, 111, 1,
But
1,
it's
0.
up counter, no?
It's a 7 we are getting. Q bar. Okay, wait. Here directly Q values. Okay, okay, fine. Q value, Q bar means what? If Q is 0 means Q bar will be 1, right? So here Q bar is high. Q bar equal to 0. Q bar equal to 1 means it's a 0. So that's why it is changing with respect to this 0 signal. Q bar means 0. And this Q signal again here 1 means 0. That's why it is changing with respect to the negative edge here. 0. 1 means it's a 0. Understood now? Suppose Q equal to 1, Q equal to 0. Before 1, we connected like this directly 0 to 1. But now we need to connect a 1 to the clock signal because Q bar it is 1. So this 1 we need to connect here and here also. This 1, this 0, whatever this value is there, we need to connect here. That's why it is changing like this. Understood? Or any doubts?
Can you repeat once the diagram?
Diagram is same. This diagram is correct only, not wrong. Actually, before we took 0 here, Q is directly connected. Q directly connected means to this positive edge of the clock only we are changing the values, so we got properly. But we are not connecting Q directly to here. Q bar we are connecting. Q bar we are connecting means what? If Q is 0, Q bar will be 1. Okay, so if Q is 0, this for this 1 it is reflecting here. Every 1 we need to consider here. Okay, that means negative edge, getting negative edge. If it is 0, positive edge. If it is 1, negative edge. That's why for every negative edge we are changing the value, Q bar value. And here it is a 0 means here it will be 1. So for this negative edge we need to change. Again here 0 means it will be negative edge for this. And again 0 means it will be negative edge for this. Q bar. Or else directly draw Q bar here itself. Same you will get the value. Okay. Clear?
Yes.
Others?
So Prasanti, like in short, can we say that asynchronous up counter will be triggered with by the negative edge of the clock? I mean, like in the second flip flop, it will be triggered by the negative edge of the clock, and
No.
in the
Wake up.
up counter, ne- in the
It's
down
not
counter.
it's not negative edge of the clock. It's just reverse
Yeah.
value of Q0. Clock is
Okay.
fixed here. Positive edge of the clock. Clock is fixed here. Only single clock.
Mm-hmm. Okay.
But the values are triggering here. 0 to 1 complement.
Okay.
Yeah, instead of this Q, directly take Q bar value and check.
Yeah.
Okay. In the same way, 3-bit asynchronous down counter using negative edge of the flip-flop. So here. So here also same negative edge of the clock. So here every negative edge of the clock, and here. Sai and another girl, are you able to understand?
Yeah, ma'am.
Okay, Rakshita. Aditi? Okay, so at positive edge of the clock, t is equal to 1, q value. What will be the q value? So at this negative edge of the clock, initially q is 0. Next negative edge of the clock, 1. Next negative edge of the clock, 0. And then next negative edge of the clock, 1. Next negative edge of the clock, 0. Next negative edge of the clock, 1, 0, 1, 0, 1, 0. Okay. Now here also Q bar is connecting. Q bar is connecting means what? Reverse. Before it is a pause edge, it reverses to neg edge. Now it is a neg edge clock, but it will be reversing to pause edge. So every pause edge clock, the output will be changing. So 0 for this positive edge of the clock, 1, and then here also 1, 0, and 1, 0, 1. Okay. Next, here we got positive edge of the clock out, but coming to here, it will be reverse, negative edge of the clock. 0 here means here 1. So edge also reversing. Okay. So that's why next, for next negative edge of the clock here, here and here, output will be changed. So 0 for negative edge of the clock, 1 for negative edge of the clock, 0, negative edge of the clock, 1. Clear everyone? Hello.
Yeah,
Okay. So 0, 0, and here 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, double 0, 1, sorry, 0, 1, 1, 0, 1, 0, 0, 0, 1, triple 0. Down counter, negate trigger. 7, 6, 5, 4, 3, 2, 1, 0. Same up counter. Up counter is a direct signal. You can set like this, up counter. So no need to interchange pause edge, negate like that. You will get the direct values for up counting. Like this. Okay, up count negative trigger. For every negative trigger, directly you will get the values. No need of interchanging. See here, clock negative edge, and here Q0 negative edge, and here Q1 negative edge. Like that, directly values will be changed. Directly we are connecting Q2 negative edge. That's why. Okay, clear till here?
Ma'am.
Next, asynchronous up or down counter. Both will be in the same circuit using a mode signal. In parallel adder, parallel subtractor, by using a mode signal, we did, right? Just selecting high or low. In the same way, we use up or down counter. So down bar equal to 0. So down will be activated, active low signal. Then down counting. If up equal to 1, up counting. So multiplexer we are connecting in the middle of both the flip-flops here. Okay. Till now, if you observe before up counter or down counter, what is the major difference between up counter, down counter? Whether connecting to Q directly to clock or Q bar directly to Q. Okay, these two difference. So in the same way here, if it is a down counter, all are positive edge trigger only. Okay, go and check positive edge trigger. Pause edge trigger. Up down counter. Down counter means Q is connecting to clock. Up counter means Q bar is connecting to clock. Okay. Same here. Down equal to 0. That means up 0. Multiplexer 0 selection line. That means 0 signal is Q. So Q will be connected to here. And here also Q will be connected to here. And here also Q will be connected to here. Okay. It will be working as a down counter. If up by down bar equal to 1, then this selection line, first selection line. So here Q is connected to here. I mean Q bar is connected to here, and here also Q bar will be connected to here. How you will write the program in Verilog? You need to create the multiplexer in structural modeling and also flip-flop, T flip-flop individually, and in the main structural program, take 3 copies of multiplexer, 4 copies of flip-flops and make the connections. Based on the test bench input signal, mode signal, you can control up and down values. So it will work as a up-down counter using Verilog HDL. Tomorrow we will write some programs in structural modeling. Then only we will discuss some logical questions. Okay. And next, asynchronous completed. Synchronous counters. For synchronous counter, we cannot directly connect like that before. However, we seen we need to follow some process for synchronous counters. What is that process in the sense? First of all, I'm taking 3-bit synchronous counter. So for 3-bit synchronous counter, it counts from 0 to 7 up counter. Okay, 0 to 7 up counter. First of all, we need to take the truth table here, present state to next state. Okay, based on the present state to next state, we will get the output. I will share you the reference videos. Actually, in every sessions, I won't explain these things, but maybe you forgot, maybe you have studied a lot back. So that's why I'm explaining these things. Okay. I will share you the some recorded sessions or some reference sessions for more clarity. You can go through that. You can refer those session, but I will explain once. Okay, normally just. So 0 to 7. 0 to 7 means what? We need to take each count. 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 6 to 7. Again, after 7, it comes to 0. Okay. So, first we need to draw present states and next states. Okay. So how many number of inputs are there here? T0, T1, T2, or Q0, Q1, Q2 outputs, present state. Q0, Q1, Q2. Next state Q0, N, Qn1, Qn2. Like that you can take the representation. Okay. So if present state is a 0, if present state is 0, that means all are zeros here. 0, 0, 0. Then what is the next state? Next state is 1. So 0, 0, 1. And if present state is 1, 0, 0, 1, then what is the next state? 0, 1, 2. If present state is 2, 0, 1, 0, then what is the next state? 0, double, 1. If present state is 0, 1, 1, then what is the next state? 4. After 3, 4. If present state is 4, next state is 5. 1, 0, 1. If present state is 5, next state will be 6. If present state is 6, next state will be 7. If present state is 7, next state will be 0. Like this, you will get the present state, next state, truth table. Okay. So based on this, you need to write the output expression. Okay. You will get the output expression for Q0, Q1, Q2. Okay. For Q0, you will get the value as a 1. So directly we will connecting 1 here. Okay. For okay, not for okay, for T0, T1, T2, you will get the values in terms of Q0, Q1, Q2. Okay, what you will get? T0 equal to 1 you will get. So directly we will connecting T0 equal to 1. For T2, you will get the input value as Q0. That's why directly we are connecting Q0 to T1. But for T2, you will get the AND operation of Q0 and Q1. And of Q0 and Q1. That's why we will connect here this AND signal. And like that, if you take one more, you will get one more AND. This input, and first input. All these 3 inputs to one AND gate, and like this. It goes, the flow will be it goes like that. Okay. So I will share you the reference video. In that clearly you will get the how to write the expression. From that expression you will be drawing this circuit diagram. From this diagram you already know how to draw the waveforms. All are synchronized with the clock. All Q0, Q1, Q2 all will trigger at a time with respect to the same positive edge of the clock or same negative edge of the clock. T will be 1 for all cases. And Q0, Q1, Q2 automatically will get the output. These are synchronous counters. Clear, everyone? Hello.
Yes.
Synchronous up counter, synchronous down counter, and shift register counters. Ring counter and Johnson ring counter. So ring counter is nothing but it's like a shift register type. Here suppose there is a 6-bit ring counter. 6-bit means total 6 number of clock cycles it will be counting. Here we will have 2 asynchronous signals. Normally we have 2 asynchronous signals. One is a preset, one is a clear. Whenever preset is high, output will be high. Whenever clear is high, output will be 0. These 2 are active low signals. That's why we will put here as a bar, and here also we'll consider as a bubble. All these bubbles. Okay. In ring counter, first flip-flop will always connect to the preset. Okay. And remaining all flip-flops will connect to clear signal. That's why we will get the output preset. Preset high means automatically we will get the output as a 1. it go to set state. Remaining all clear. If all clear signals are high, we'll get all as a zeros. Remaining 5 as a zeros. Now we will get the loop like this. This Q will be connected to feedback to the D input. So in the same loop, it will rotate. How we will connect the two buffers or two NOT gates in a back-to-back connection. So there will be no controllability. The feedback will be like 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. Like that. Same here. This 0 will be coming to here. So 0, this 1 will be shifted to here. This 0 will be shifted to here. This 0 shifting here, here and here. Again, this 0 will be shifted to here. 1 will be shifting. This 0 will shift here. 1, 0, 0, 0. Again, this 0 back. 0, 0, 1 like this. Okay. To get the final same value, this 1 is getting here. Again, this 1 should be shifting to here. So 1, 0, 0, 0, 0, 0. So whatever the input we have applied, output also same. At which clock cycle? At 6th clock cycle. Okay, at 7th clock cycle. So after 6 clock cycles, at 7th clock cycle, we will get the same value. Okay, that's why we will call it as a mod 6 mod n counter. If n is equal to 6 number of flip-flops, then it count n number of clock cycles. If n equal to 4, it count 4 number of clock cycles. Okay, so that's why ring counter we call it as a mod n counter. Johnson ring counter reverse, twisted ring counter. We can also call as a twisted ring counter or Johnson counter. In Johnson counter, this Q bar, whatever the Q bar is there at final stage, this Q bar will be connected to here. So here reverse operation we will get. If Q equal to 0, 1 will be connected to D. So here we will get assigned 1 every time. Okay. So that's why in that case, we will get the multiple signals like this. So if you observe here, by default, all will be connected to clear signal. So this 0 output will be 0. And here as we are connecting 0 to 1. Okay, so that's why 1 here, 0, 0, 0. Again, this 0 is connecting here because of reverse bar, Q bar, 1 will be getting here. So to get original value, it will take 8 number of clock cycles. So all zeros. After 8 number of clock cycle, at the 9th clock cycle, we will get the output as a all zeros. Okay, this is Johnson ring counter. That's why we call it as a 2n. Modulo of n bit Johnson counter is 2 into n. Suppose here 4-bit means 2 into n 8, mod 8. If it is a 4-bit, 2 into 4, mod 16 Johnson counter. Like that we call. Okay, clear everyone till here?
This is not clear. I mean, how to 8 states are coming? Like
What?
in this Johnson counter, how 8 states are coming for with 4 D flip flops? Like
Edge trigger?
no. I'm asking like with 4 D flip flop, how 8 states are coming? It's not clear
How?
to me. Yeah.
How? I didn't understood that word.
I mean to say like this 8 states are coming, right?
8
Here.
states. Okay, wait. I'll explain. Eight states. Why? Because before in ring counter, directly this Q value is assigned here. Okay, so initially 1,000. Suppose ring counter means this 0 directly assigning to here. So this 0 is getting here, 1 is here, again 0, 0. So again this 0 is getting here, this 0 shifting to here, and 1 is shifting to here, 0 is shifting here. Again, this 0 is getting here, this 0 and 0, 1. So 4 clock cycles here, and next clock cycle 1 triple 0 in ring counter. At 5th clock cycle, we'll getting the original value because directly Q is connected. But here in Johnson counter, Q bar is connecting here if you see. So same 1 triple 0 I'm considering. Q bar, this is a Q value. This 0 is a Q value. Q bar means how much of 1. So 1 is getting here, this 1 is getting here, this 0 is getting here, and this 0 is getting here. Again, this 0 is a Q. Q bar means 1. So this 1 is getting here, and this 1 is getting here, this 0 is getting here. And this 0 bar means 1, 1, 1, 1. And again, this 1 bar means here 0. This 1 is assigning here, this 1 is getting here, and this 1 is getting here. And this 1 bar means 0. This 0 is getting here, and this 0 1 is getting here, and here also 1. And this 1 bar 0. This 0 is getting here, this 0 is getting here, 1. And this 1 bar 0. All zeros now. So initially, what value we applied? 0. So whatever the value we applied here, whatever the value we'll get here at 8 clock cycles, after 8 clock cycles. That's what. See here. Initially, all are zeros. After doing this functionality at the 9th clock cycle, after 8th clock cycle, we getting the same repeated value. If we send this one again to here, we will get 0. This 0 will be reflected to here, and this 0 will be reflected to here, and 0. Did you understood now?
Yeah.
Clear, others?
Yes, Prashanti.
Okay, so this is all about counters. Glitches in the sense glitches and hazards. Glitch is nothing but where we will get in some cases sudden change. We call it as a sudden change. Okay, suppose here static, it is a static 0 hazard. First one is a static 0 hazard, static 1 hazard, dynamic hazard. Okay, so in static 0 hazard, how it is looking like? It should be 0 constantly, but sudden glitch is getting here. And static 1 hazard, it should be constant 1, but sudden glitch is getting like this. And dynamic hazard, more number of glitches, sudden glitches are getting. Normally, it should flow is like this clock. It should flow like this 0 1 0 1. Okay, but sudden glitches, that means 0, suddenly 0 1, instead of going straight 1, suddenly some glitch is getting like this. Instead of going straight 1, suddenly we'll get glitches like this, suddenly 0 to 1. Like that, whenever it is moving to 1, suddenly some glitch will get like this without moving constantly. Okay, that's what we call as a glitch and hazard. Okay, so why we get, in the sense, there are 3 cases. How we can eliminate these things means, suppose if there is a mismatch in the delays. We already discussed this example also before. So when do we get these hazards? Like there are 3 number of gates or any number of gates. Okay, so suppose here 2 nanosecond input is a 2 nanosecond, and here input of this gate delay is 2 nanosecond, and here also gate delay is 2 nanosecond. Okay, AND gate, this output here, output is getting from this side propagation delay 4 nanosecond, and B side also propagation delay 4 nanosecond. Okay, so if you apply these two inputs, we get the output at 4 nanosecond. But C, at C type, we don't have any delay. We have 0 delay. Okay, this C value will get at 0 simulation time only. But for this A and B value, getting at a 4 simulation time. Okay. So in this case, output will get mismatch, or else you can also observe like, suppose A and B, 0, 1, 0 into 1 is getting at the 2 time units. Okay. C value is 1. This C value is getting at a 0 time unit at this point of time or at this point of time. Okay. If it get at this point of time, automatically will get 1, right? If it is working at some edge of the clock, we are getting 1 at this point of time. Okay. But that is not constant. Why? Because next, within 2 seconds, this value is updating within just fraction of seconds. Okay. So this 0 is getting 0 into 1 or 0 plus 1. Suppose if you consider it as an AND gate, 0 into 1, output will be 0. So to this 1, it is suddenly, it should go like this, but suddenly it is going to 0. This sudden change is getting up because of the asynchronous input signals. Okay. Asynchronous input signals, in the sense both are not getting at the same time. These both inputs are not getting to the OR gate. There is a minimal difference between inputs. So output is getting some input, output is getting here for this some input at first time, and within seconds output is getting some other value for these inputs. Okay. So to avoid this type of sudden change, sudden change, that means glitches, we need to put extra delays. Suppose if you we used buffer. Buffer means input and output both are same, right? So we can put any number of buffers. There is no functionality change. If you put not get, overall functionality will be damaged. We'll get the error. We don't reach the actual value. But buffer means we will have the actual value even if you put hundreds of buffers. Okay. But buffer delay will be there because it's also a gate, right? So it has some delay. 1 nanosecond delay will be there. So to equalize the value, input value here at 2 nanosecond, and here also to equalize the time 2 nanosecond, we are putting two buffers. So 1 plus 1, 2. So now this value from first output and this input value, both inputs will come at the same time, and output is also getting at same time, so that we don't get the glitches. Okay. But if it comes at 1 is coming at 0 simulation time, again 0 is coming at some within fraction of delay, means in output sudden glitch will be happen like this without moving constantly, sudden change like this. That's what we call as a glitch, and how we can avoid means like this. There are other two models where we can use some K-map and flip-flop at the output side. K-map, this is not mostly used, very rare. Just whatever the redundant terms are there, we need to use these redundant gates, and then we connect. That is a K-map. And next method is using D flip-flop or any flip-flop. D flip-flop is also same as a buffer, right? It stores the memory, and also output will be changed only with respect to the positive edge of the clock or negative edge of the clock only. So that's why in that cases we can avoid the glitches. Okay. So if you see here, from this before output, we are getting this sudden change and here and here. But to this output, if we connect a flip-flop, output will be changed with respect to the positive edge of the clock only. Even input is changing here, suddenly it doesn't reflect. Straightly we get 0. And this sudden change also will not reflect at the output. We get the straight output. Okay, these are the 3 methods to avoid the glitches. Clear, everyone? Next, finite state mission. Finite state mission mostly next weekend. By next weekend we will start. Okay, any other doubts? What about Verilog assignment? Have you completed? Second assignment. Hello.
So only one is completed, Prasanti.
Okay. So you can do whenever you get the time. Okay. But try to complete. Don't put any pending works. Okay.
Yes, yes. Yeah.
Yeah. Okay then. Thank you all.
Thank you.
Thank you, Prashant.